Okay, good morning, everybody, and welcome to the Wednesday morning session. And it's a great pleasure to have Renate Loll from Radboud University in Nijmegen talking about really non-perturbative quantum gravity and its applications. The stage is yours.
Okay, good morning, everyone. I should start by thanking the amazing organizing team for doing so much work to get us all here and well organized. So Bianca is not alone in talking about non-perturbative quantum gravity. There's also me, and that's what you will be treated to in the next hour. So I started by giving some impressions. This is an impression of what space-time may look like on very, very short scale, so very, very non-classical. And nevertheless, we can kind of extract, by performing clever experiments, we can extract some geometric properties from it, some of which even remind us of classical manifolds, space-time manifolds. Okay, but now let's get to the beef of the matter. Now I should be. Does it want to change slide? Oh, it's not connected. No wonder. Okay. Okay, but I should be able to advance it here, but it doesn't do it. Maybe click on the slides. That doesn't do it either. Okay. Let's get connected. Oops. That doesn't react either. It's very stubbornly on this first page. No. Okay. So to put the whole thing in context, so here's in a condensed way what this is about. I'll be talking. So there is a functioning theoretical and computational framework. So that's lattice quantum gravity for you, formulated in a particular way in terms of causal dynamical triangulations, of course, the theme I will return to, CDT, which describes four-dimensional quantum gravity as a, number one, non-perturbative, but also diffeomorphism invariant quantum field theory of dynamical geometry. So the dynamical is also important, and it produces quantitative results, something quite. It's minimalist. You could say it's the more or less straightforward quantum formulation of general relativity without any exotic ingredients or symmetries, extended fundamental objects, think loops of strings, or a proliferation of free parameters. And it is accessible to numerical experiments, which allows us to extract those quantitative results. So its unique strengths, perhaps also in emphasizing what may be important here for the audience, contrasting to some of the things you have already heard, it has opened a non-perturbative, but as I will explain, nevertheless, physical perspective on quantum gravity. So it's distinct from and complementary to perturbative and effective field theory formulations of quantum gravity. And that also dictates the kind of questions one can pose quite easily in this context and the potential answers, and therefore phenomenology down the road it can address. And I'll give you, of course, in a nutshell, a progress report of the things that have been happening in this approach. So here, for people who want to fall asleep right away, here are some key takeaways, which I'll, of course, expand on in the rest of the talk. So after quite some time, we have finally learned how to put four-dimensional quantum gravity, and that will mean the gravitational path integral on the lattice correctly, and thereby investigate it beyond perturbation theory. So the best lattice methodology, up to this point, I would claim, is based on this specific method of causal dynamical triangulations. But that's a technical tool. It's a regularization. And importantly, it's manifestly coordinate or diffeomorphism invariant. And the way to think of it is really a gravitational analog of how we formulate lattice QCD in terms of holonomy. So So that's Wilson's formulation, and the beautiful feature of that is that you work with these link holonomies, and you contract them in such a way that you have an exact version of the gauge symmetry that you had in the continuum. Just it doesn't live everywhere, but it lives only at lattice vertices. So my method of putting gravity on the lattice, you may think of as doing, constructing the variables relative to the lattice in an appropriate way so that it is indeed manifestly coordinate invariant. So having done that, we obtain a unique window on very short scale Planckian physics that we haven't been able to explore. And we explore it in 4 dimensions numerically and study the behavior of observables that characterize this realm of physics. So what we'll see among the important results this has produced is kind of an emergence of space-time. If you sit in an appropriate region of the phase diagram, understood in a statistical mechanics way, of the system that I'm putting, have regularized on the lattice, and whose continuum limits, of course, I'm interested in, not the lattice itself. And it gives us a new perspective on what quantum gravity can deliver, I say here. So really, the questions that can be posed and answered in this realm naturally. So as a kind of technically new feature that has, again, opened the way to new observables, there is a notion of curvature we have relatively recently been able to construct, which has nice properties under renormalization, which you can put on the lattice, which allows us to construct more observables than we had been able to in the old days, and that can now inform our understanding of the very early universe. So that means making potential connection to real physics. That was one of the questions that were asked, right, by participants. How does all this Planckian nonsense ever relate to real physics? So here is an opening toward early universe cosmology. Now, this whole framework you could characterize as doing quantum gravity without G mu nu. What do I mean? In the realm I'll be looking at, there is no tensor calculus is not available. I'm sitting on these crazy geometries like the one I showed on the previous slide. So we have to resort to other ways of doing, gravity and describing geometric structures, and we will have to rely on, in a mathematical sense, stuff that goes beyond classical pseudo-Riemannian mathematics, right, as it was founded in the mid-19th century. So we have to go beyond that in a mathematical sense. Okay, here, let me advertise. So if you are, most of you, of course, are experts in quantum gravity, but here is a recent review on kind of quantum field theoretic approaches like this one, but there are, of course, others. Yeah, sure. It's not no, it's not connections, but you'll see on this slide. Yeah. Yes. Einstein's equation, where you see there is a non-commutativity in, I start from a quantum regularized theory. So, obviously it will, as will be on this way, it's motivated by how classically one can describe geometries through lattices. But then, of course, in the quantum theory, I first have to take proof that there is a continuum theory, and of that continuum theory, I have to examine the observables. And for these observables, I then have to ask, do they have meaningful classical limits? And I'll give you some examples of observables that do. Right? So well, there will be many unknown features, coming along. So suppress anything but really, really urgent questions, because otherwise I'll never get to the end. But I mean, thank you. It doesn't mean they are not good questions. They are. So what does it mean to put quantum gravity on the lattice correctly? Okay, so what's the general kind of standard philosophy that we inherit from something like, lattice QCD, or even statistical mechanics, which we regularize on lattices. So this lattice acts as a regulator. And we have a cutoff. So it's a short distance cutoff. So here I've just drawn a piece of a cubic lattice, right? And it's characterized by kind of the length of these lattice edges. It's A, and that for me is a UV cutoff. So you study then properties of this thing for finite A, but then you systematically search what happens and do other interesting things that happen and that kind of survives this continuum limit as I take A to 0 and attain what is called universality. So forgetting about the details of the regulator, I put in, the shape of the lattice, how I, put in my variables on there. And that typically happens in standard systems near second order phase transitions. Yeah, so where you then can define, if all goes well, your continuum theory in a specific approach to such a second or higher order phase transition point. So this was, of course, known for a long time, and people have been looking at quantum gravity for a long time. And starting at the end of the 1970s, people also looking at great successes of putting gauge field theories on the lattice, tried to imitate the same for quantum gravity. So what they did was a kind of, have a shot at it by simply putting variables for gravity on a fixed 4D lattice. And well, with some motivation, theoretical motivation in mind. And then, of course, well, you cannot, compute things analytically, but then say Monte Carlo simulating the systems. So unfortunately, they never saw anything interesting. So I should say briefly, so what is here, it came already up in your questions, Ravan. So what one does here typically in this strategy, one uses a first order formulation. Why? First order formulation contains connections. So the connections are my gravitational analog of the gauge connections for QCD, say. So that makes it look more like QCD. And then you also work with holonomy variables typically. Unfortunately, you also have something like Vierbeins floating around. And that's part of what makes it nasty. But to cut a really quite long story short, these systems were extensively studied, but nothing interesting was ever seen. And the question is why? And there is a competition of good reasons for why this probably never could work. So the biggest one is the broken diffeomorphism invariance. So you just naively, take your continuum formulation and you just put your connections, associate your connections with the edges and your Vierbeins with some other sub-elements of the lattice. And then, you go. What happened to diffeomorphism invariance? It's completely gone out of the window because that's your rigid lattice that's just sitting there. So you just don't know what happened to it. So therefore, it's very unclear what degree of freedom you're describing here. Plus, of course, we know, of course, so you have to, on the lattice, well, you have to go Euclidean. So what people were actually discussing was a Euclidean version. So Euclidean quantum gravity typically, and that of course has an action that's unbounded below. So that of course induces an instability which you don't have in QCD. So what happens to that? How do we normalize, regularize the non-compact directions of the Vierbeins? How do you treat the fact that this Euclidean thing maybe has nothing to do with the Lorentzian story? Anyway, so this didn't lead anywhere. So what I want to say in not too many words, there is a slide later that addresses some of the technical issues, is that these things have now been resolved in this new type of formulation. And a key to the new type of formulation is what I call a geometric, less naive regularization. So what you do, you take your cue from an old idea of Reggie's from, the distant past, in a paper called General Relativity Without Coordinates, where he defines what we now call Regge calculus. And that's the idea which he used classically to start with. His idea was, can we just do classical GR, find solutions in a way that completely eliminates the gauge freedom I have because of the diffeomorphisms, and he got to this lattice formulation. So what you do classically, you regularize, you approximate your classical manifold plus Lorentzian metric by a piecewise flat object, which is most easily visualized in 2 dimensions as a regularization or a triangulation in terms of building blocks that by definition are flat on the inside, and then you glue them together according to some gluing rules. So you get what's called a simplicial manifold. So what are the data that describes this? Well, the edge lengths of all these triangles, of course, they have to be glued together, to equal edge lengths to equal edge lengths. So this is my Li squareds here. And telling you the connectivity of this object. So which triangle am I gluing to which other triangle? Now, there are no coordinates anywhere, so it doesn't carry any action by the diffeomorphism group. Yeah. So, and he just showed how one can write down the Einstein equations in this framework. And of course, people who were trying to do quantum gravity, some jumped on this idea and said, okay, can we use that to make more sense of the path integral, the gravitational path integral, also getting rid, in a nice way, eliminating the diffeomorphism invariance. That, of course, causes me problems in the continuum. So that's what I mean by a geometric regularization. So the method I told you about, so the dynamical triangulations, or the Lorentzian version, which are the causal dynamical triangulations, also relies on that idea in a particular way to really make sense of the formal path integral. So I'm writing down here just this path integral in a formal continuum notation. So it's pure gravity, at this stage. So to explain this idea. So here is just some to be specified functional measure over geometry. So what do I mean by geometry? I mean an equivalence class up to 4-dimensional diffeomorphisms of Lorentzian metrics. So that's kind of the physical thing. And each one of them in this formal path integral I weigh with e to the is. My favorite version of the gravitational action. Yeah. So this is what people call a sum over histories. So an important here, there is an I there. So this is really still the Lorentzian object. Now, using this Regge idea, you substitute this formal, integral over all metrics, or rather geometries, by the concrete sum over triangulated objects, which approximate curved Lorentzian manifolds, spacetimes. Yeah. So these are my triangulations T, and they're defined in terms of the edge length and the connectivity. Yeah. So they form really a regularized version. Gosh, why am I going back to the beginning? They form a regularized version of the space of, oops, yeah, no, I was already here. Apologies, I will learn how to handle this. Okay, yeah, quick question. This is all totally, right. In the continuum, people argue for, say, the de Wit measure, right, which is classically, well, of course, it's not immediately clear how that would work in a non-perturbative way, but the measure I'm working with can be argued to be indeed a natural variant of that. And what it is more, it's a democratic measure. So it will essentially, of course, apart from the weight factor that knows about the action, it will just give equal weight to all the geometries, unless they have special symmetries. And then they will get a smaller weight. So this exactly reproduces an aspect of the de Wit construction, but which is classical, however. Right now, it's nothing. It's nothing. I will be later on the lattice. Everything will be completely dimensionless. Oh, no. You're talking about quantum calculus. That's not what I'll be doing. You'll see. Of course, on the lattice theory, everything will be dimensionless, but of course, when I put in a physical interpretation, dimensions will be regained during renormalization. Yeah. So dynamical triangulations make use of this idea, but unless if you know it, Regge calculus and quantum Regge calculus, which are also ways of trying to use the Regge idea in the path integral, we are using building blocks whose edges are all of the same length. So basically, you have one type of building block, and then you may say, okay, so where is the sum over all different geometries? It arises by gluing them in distinct ways, in geometrically distinct ways, and counting each one once. Now, since we are Lorentzian, it turns out the totally equilateral building blocks are not the most natural thing to do, but it's useful to distinguish between space and time-like edges. And here I'm giving to you one of the two types of building blocks that are used to formulate the gravitational path integral in 4 dimensions. So the red ones here are time-like edges. The blue ones are space-like edges. So their L squareds are smaller than 0 or larger than 0 with my convention of symmetric signatures. And this is a Minkowskian building block. So it's really a piece cut out of flat Minkowski space by definition. So for instance, if I want to draw a light cone, I know where it is everywhere in this little thing. And what governs then the geometric data are for the individual building blocks are just the 2 lengths. So they're the same for all blue lines, and they're proportional to this lattice UV cut of A squared. And there is a relative minus sign between the LT squared and the LS squared. And I'm leaving myself a freedom to put here an arbitrary positive alpha. Why is that clever? So alpha is, in this Minkowskian Lorentzian picture, is larger than 0. My Wick rotation will consist in rotating this parameter alpha to minus alpha in the lower half complex alpha plane. And then it will turn any Lorentzian object, which I'm putting into the path integral, into the regularized version of this path integral, into a, if you like, Euclidean object, but a particular one, because I will also give you gluing rules that make on the Lorentzian side everything into in a causal sense into piecewise flat structures that have nice causal properties. I'll get to that in a second. I mean alpha going to minus alpha because it's squared, all the lengths are squared. So I'm working with squares because that allows me in an easy way to distinguish between time and space-like. So I just work with this alpha, and it's always real. Well, it's not real. I continue it through the alpha plane, and then of course I have to discuss what happens to the action, which I'll show you on the next page. You don't know. No, you don't know what I give you for the action. The Wick, everything is fine with the Wick rotation, but I have to show you the action. So before I do that, I just want to emphasize that what one is doing here is really something very non-perturbative. So you're not summing over objects that individually, look kind of like classical things with some little wiggles. You are summing over objects that, morally speaking, look like these crazy, things. I mean, this is comes from a 2D model, but morally speaking, that's what they look like. They are kind of higher dimensional analogs of, the nowhere differentiable path of the Wiener measure, if that analogy helps you to understand what I mean. I mean, that one uses just in the path integral for the non-relativistic particle. So in 2 dimensions, to the extent that in 2 dimensions, now mathematicians have done the Euclidean path integral over objects like that and shown it has a nice continuum limit that's called the Brownian sphere. So there is a quantum object that exists in the limit, and in 2D you can actually, in a mathematically rigorous way, get there and study its properties. And genuinely, it's a higher dimensional generalization of this Wiener measure. That's very familiar. And of course, what we're trying to do is to do the whole thing, number 1, with Lorentzian geometries or Wick-rotated Lorentzian geometries, and in 4D, where we don't have such mathematical methods at our disposal, but that's still the story. Yeah, and you might ask, how on earth can I superpose such object and get anything that has anything to do with gravity or space-time? Well, it turns out to be possible. So here's the action that Neil asked about. So on the left here is still, again, the formal continuum path integral, where for definiteness, I've chosen now a simple Einstein-Hilbert action with R and a cosmological term. And what CDT is making this kind of formal statement of intent into a really well-defined, from a mathematical point of view, regularized expression by putting in, instead of this sum over all integral over geometries, a sum over causal triangulations, which are made from my 4D building blocks in such a way that each individual history that contributes to this sum has a nice causal structure. What is this causal structure? It's a kind of a lattice analog of global hyperbolicity. So what you're doing is, here's a little, 2+1 dimensional idea. So you're stacking your 4-dimensional building blocks in such a way that the light cones are all aligned in a way, so there is an overall time direction, so there are no closed time-like curves. Yeah, and there is a kind of minimal way of arranging this as a restriction on the path integral histories. A priori, there is no reason for doing this, but if you don't do it, we get Euclidean quantum gravity, and it turns out, as far as we know until now, not to have a very interesting continuum behavior in 4 dimensions. If you require this causality restrictions, if you like, on the individual histories, which one can only motivate by appealing to causal structure as maybe something desirable, that is a total game changer, and that leads to all the results I'll be talking about in the remainder of my talk. So coming back to the form of the action, right? So here I have actually set A equal, this is a lattice spacing equal to 1, as I would usually do on the lattice, because everything is dimensionless. So it turns out that if I regularize, take this as my bare action and regularize it, use it on these rigid geometries, this is what it evaluates to. So the important thing to notice is this is a linear expression in counting variables. T is a triangulation, and D is a number of D-dimensional triangular building blocks contained in that triangulation. So N naught of T is the number of vertices it has, and 4 is the number of 4 simplices it has. And the 4 ones are one of the 2 subtypes. Yeah. So just to exhibit to you the functional form of the action is super simple. Someone giving you a geometry, it was never as easy as in this framework to work out what the action is. You just count these building blocks and you multiply them by these bare coupling constants. So about which I want to say one thing more. So this is in disguise a cosmological constant term, because it's a 4-volume, and kappa 4 is essentially a lattice version of the cosmological constant. So this node, in order for this whole thing to work, has to be larger than 0. So that is not a larger or equal, this is just underlined. Yeah. And so, but this is just a bare cosmological constant. I want to point out the way these path integrals work, and the way you take a continuum limit from inside the region of convergence dictates also the sign of the renormalized cosmological constant. And this turns out to be also has to be larger than 0. It's a free parameter of the theory, so it could be tiny, tiny, but it's larger than 0. So we can do DS, we cannot do ADS. It doesn't work. Does it have a deeper significance? We can argue about this, but this is part of that, is a feature. Yeah. Yeah, so my primary concern here is to evaluate the path integral non-perturbatively. So in a way, what I'll be finding will be if you like, the ground state of this non-perturbative system. And the ground state will be the state of lowest Euclidean action. And in that state, I will then evaluate certain observables that will characterize what this state is about geometrically. This state will turn out not to be a black hole. Okay, so but that's in a way a dynamical outcome. Okay, so but thank you for the question. So the path integral histories, so they have this well-defined causal structure, and what we are working with on the computer are, just a second, for simplicity, compact spatial slices of topology S3, and there's a time interval, which again, typically for simplicity, we cyclically identify in a way that, of course, one has to check, but that kind of bulk observables, will not be affected in a grand way. So that's the system we are studying, and we can put on a computer. So that's one of the key things here. I said, quantum gravity, well, it's a subject I've worked on for far too many decades, has always suffered from us arguing about, what we would like to compute if only if you could compute anything. Now, so this gives you a tool to compute things, and that makes many questions also of a slightly theoretical conceptual nature much more concrete, and you will that gives you new insights. So, but in order for this to work, to put things on the computer, to run Monte Carlo simulations, we cannot work with the complex amplitudes, but we have to use this alpha going to minus alpha trick. So you might say, oh, but then you are in fully Euclidean. That's not true, because the geometries I constructed in the Lorentzian, I construct them according to Lorentzian gluing rules. So even after I rotate the geometries, individually to Euclidean signature, they remember kind of, that they came from causal geometries. So if you look at them in the set of all Euclidean triangulations, they're just kind of a small subspace of measure zero. But of course, there's still very, very many of them. And that allows us to derive conclusions from the system that are totally different from those when you do, full Euclidean quantum gravity, where all these non-causal objects are they're everywhere, and they're full of topology changing amplitudes. Yes. Mm-hmm. Yeah. Well, yeah, so the other one is a 3-2. So the 3-2 is still in here. In the N4, we add the 2. So it does depend on both of them, but not in a symmetric way. But I mean, that's, well, just because they're different geometrically. So that is not, it's not a significant, it doesn't mean anything specifically. So then what I said, we are not interested in the lattices per se, but in taking continuum limits. So that means sending A, the UV cutoff, to 0, sending the number of total building blocks to infinity, while that's the typical thing we require, having a finite physical volume left invariant, which I call V, a 4 volume. Yeah. So this is A to the 4. So you can think of that really as a dimensional thing when I put in units that are tied to this lattice cutoff A. Okay. So we can run Monte Carlo methods. And of course, we've been doing this for the last, since the early 2000s. And lot is known about this entire system. So it has a phase diagram, yeah, as you would expect. And we are doing, this is already for an infinite volume limit, or extrapolated to it, and we have a phase diagram that contains various phase transition lines. First order transition is here. There's a second order phase transition line, and there's another second order phase transition line, and various phases of which A and B turn out to not have any macroscopic interpretation. They're not physical for gravity purposes, as far as we can tell. The interesting phase for us is this one. It's the de Sitter phase. And Here's this little, I get back to this little drawing, it has something to do. It generates something that looks has properties of the zeta universe. So let me not talk about this phase. This is something different. I won't get to that today. And so we are sitting, in this phase, and we can try and approach a second order phase transition line. So from that point of view, it looks like a, statistical mechanics system just for gravity. Of course, there are subtleties hidden everywhere, but no other approach has seen higher order transition lines. So here are some for those of you who asked, let me remind you of what all the troubles are that come with the path integral for gravity. So usually, this is just the expression on the previous page. We cannot evaluate this complex path integral, well, in no form, basically, beyond perturbation theory. So what one typically then does is not to Wick rotate, as I did, but just because a Wick rotation is not known for continuum geometries, so one just instead starts from this fully Euclidean expression. Yeah. So you put in just 4-dimensional Riemannian metrics instead of Lorentzian objects, and then you say, okay, let me solve the theory and then, rotate it back in the end. Well, this program doesn't really work because this has never given anything interesting outside truncated models, cosmology, for instance. So we have instead a well-defined Wick rotation, which I explained to you in so many words. So then there is the infamous this I? Well, things conspire. No. Things conspire. The alpha dependence of this Reggie action conspires in such a way that when I send alpha to minus alpha, I pick up suitable factors that combine with this I to something that does generally give you e to the minus S Euclidean. It's in the very first paper from 1998. So it's really straightforward. So it gives you the minus sign. Everything is as it should be. But okay, even in order to get somewhere within my hour, I really have to, stop the questioning. It's very interesting. Let's leave it for the discussion. Everything is comme il faut. So I'm not doing any funny things by, rotating things in a funny way. No. Okay, so the conformal mode problem was already mentioned yesterday. And let me point out, this is not just the homogeneous mode, but it's a whole infinite tower of modes, right? So which have negative kinetic terms and therefore render the naively the Euclidean path integral, well, unbounded in a massively, so lead to an instability. So what happens here? Well, the non-perturbative aspect saves us in the sense that in part of my phase diagram, their contributions kind of from the measure, if you like, the entropy of states that counteract this, suppress this divergence, so that the final result can be stable and finite. Now, renormalizing compatible with diffeomorphism symmetry is a huge headache in any continuum formulation. So here we really have dealt with it kind of in a manifest way, and there are no residual gauge symmetries. We have this geometric cutoff. Then what about the UV divergences? Well, this thing, what does that look like here? Well, number one, so there is strong evidence that there is an exponential bound on the number of configurations. So that's good. But also we find then that we can take this continuum limit. And it seems to give meaningful results in the sense that we get a seemingly meaningful behavior of observables we study in a Planckian regime, so that are not divergent. Can we map it onto anything, in the continuum? Well, Jan and collaborators are currently busy constructing the first explicit map to a simple version of asymptotic safety. So that's the most conservative thing one might think, this could represent on the lattice, that you're reproducing, you're giving genuinely non-perturbative evidence for the existence of the UV fixed point. Sorry, no time for questions right now. Keep it to after the talk. So yeah, so what this is in detail is, of course, difficult to say, but well, these are the facts. So unitarity was extensively discussed yesterday. So what does that translate to on a lattice? It relates to the requirement of reflection positivity, which is simply a lattice version of what you require in the Osterwalder Schrader axioms to be there. It's just a Euclidean version of unitarity. So that is satisfied here for arbitrary lattices. So if there is a genuine continuum theory we can find through a limit, then it's highly likely to actually be unitary. Okay, this was my toolbox. Now let me talk about the results in my remaining time. So, of course, what catches up with us is the interesting and unusual nature of observables in gravity and in quantum gravity. So the physics of this object I'm generating dynamically in my computer, this ground state, is captured by quantum observables, which I'm evaluating in the path integral. So this is the standard way. After I've Wick rotated, right, I have my gravitational path integral. I'm resorting to a formal continuum way of writing things, and I just insert this operator in the trace. And of course, it has to be diffeomorphism invariant for me to give anything interesting on the left-hand side. So typical observables are non-local. That has also come by. And a simple example is that of a scalar, like the Ricci scalar. So why is the Ricci scalar itself not an observable? Well, because the point x, pointing to any point x, without introducing, a physically defined coordinate system is not really, it isn't well defined. Certainly not across the sum over geometries. So that's what we have to do. Of course, you could say, okay, what can I do with this quantity? Well, there are things that one can be done. Now, what cannot really be done in this Planckian realm is constructions that one uses classically or perturbatively to construct observables. So the relational observables are very, very problematic. Why? Because you don't have, this is not an analytic framework. There's no tensor calculus. So these refined functional relations are impossible to capture with the variables in the description I have here. I'm also not relying on any asymptotics or any boundaries. First of all, I'm working with a tiny system, which is kind of 20 Planck lengths across, it turns out. So anyway, I've compactified, but there is no sensible notion of, asymptotic regions. Fine, I'm describing, bulk physics, and it comes with a Hilbert space, morally speaking, that is certainly higher than one-dimensional. Yeah. So this is interesting what I've been doing. So as I said, I mean, the type of observables we have access to, they reflect the absence of meaningful reference frames, in this very, very highly quantum fluctuating realm. So this implies, especially to an audience that is used to working with perturbative and effective methods and continuum G-mu-news, what I call expectation management. So many quantum gravity questions that people say, this is, that's what I'm after, solving the black hole information problem, resolving singularities. Well, they're not easily addressed in this framework. And I would say it's a bit of a question whether they have any meaning to them in a really Planckian regime. Because what you would have to do, you would have to find a genuine kind of Planckian implementation in terms of the tools that are given to you here, and an operational definition in this background independent and highly quantum fluctuating setting I've constructed for you. So you may say, okay, well, I'm not interested in that, but well, it's a feature. So, that's again, this non-perturbative perspective I'm exposing to you. So what we have to do to work with this in a creative manner is to adjust our expectations to what can be naturally done at that level. And of course, since it's a feature, one could also argue, well, this is just what we are able to learn in a Planckian regime. It's not very much informed by, stuff that is on the pages of a classical GR textbook. All right, so what is this? What are examples of observables? Well, they're surprises. So here is, an observable that probes genuine quantum features of this non-perturbative system. It has to do with the dimension of these objects I'm studying. So is there a notion of dimension? And how would you define it operationally? As I just said, you have to. Well, it's what is called the spectral dimension. So what is a spectral dimension? The spectral dimension is a dimension you extract from a diffusion process. So what kind of spaces do you need in order to set up a diffusion process? Anything basically that has a Laplace type operator on it. Okay, so that is satisfied by our ensemble of geometries in a certain limit. So we've run, or not, colleagues have run diffusion processes on these ensembles. And the surprising feature is, when you do this, is the insight that the dimensionality of the building blocks does not determine the result. On the contrary, when people played these games first for the purely Euclidean quantum gravity, well, one was, of course, always assuming that if you get anything, it must be a four-dimensional geometry. After a while, one found out that is simply not the case. Why? Because these systems degenerate kind of in pathological ways generically. So they like, for instance, to form branched polymers. So I give you, a bunch of 100,000 four-dimensional building blocks. If you just use, Euclidean building blocks, anything can be glued to anything, then you will find that they preferably, this is entropy, they preferably align themselves into one-dimensional polymers and then branch everywhere. And that's a system that has Hausdorff dimension 2. So one of the things was, okay, can the causal version of DT, dynamical triangulations, do better? And it does. And so here, again, how can it happen? These surprising features, well, we're taking a non-trivial limit. A goes to 0, so many things can happen. And the basic mechanism here is you have kind of in a region of phase space where we see interesting kind of non-perturbative physics, you get significant contributions from kind of what I call the entropy. It's kind of the number of states at a given value of the action weights and the energy. Yeah, and there suddenly interesting new physics appears, among them the spectral dimension which you extract from this diffusion process. And in this, in our lattice framework, we were first able to show that it reduces on small diffusion times where you probe very truly microscopic features of the geometry to 2. So that's a very interesting feature. So it's a dimensional reduction that you dynamically extract from the system, and on long distances where it probes long-range properties of it turns out to be compatible with 4. So that's nice. That is like the classical limit. But on short distances, it continuously goes somewhere towards 2, and that has been much worked and talked about by many people in various approaches who've kind of partly reproduced these in their approaches. And it has been conjectured by Steve Carlev in particular to be a universal property of quantum gravity. So this is clearly not a perturbative effect that I can see anywhere when I do, H-bar perturbation theory. So it's generally non-perturbative. It's a dynamical mechanism. And of course, what could have happened? I could have found that the spectral dimension becomes larger when I go to a Planckian regime, becomes 10 or 11 or maybe even 26, right? So, but this didn't happen. So we're finding 2, but it's a dynamical mechanism. You can ask, do we know a phenomenology that relates to that? Not really, because we don't have sufficient good understanding of how matter is coupled to them. There have been some very heuristic, treatments to understand what would a dimension, a non-4-dimensional background mean for propagation of gravitational waves. So you can look these up. It's a first step in that direction, but it shows you it's not totally unthinkable that now from such a non-perturbative feature you can extract consequences on a larger scale. Okay, now most remarkable result maybe in this whole thing is this emergence of a space-time, if you like, from nothing but quantum wiggle, so which I somewhat poetically describe as quantum foam. Yeah. So the word emergence is, of course, used in an inflationary way these days. I give you an equation, and for you, the solution emerges. what I mean here is really, I have a microscopic system, kind of statistical system of these tiny building blocks with some gluing rules. And when I am in the right part of phase space and I take kind of an infinite continuum limit, the final result can be characterized by observables, some of which indeed show properties that are only known from macroscopic spaces, which I didn't put in by hand in the first place. So the most interesting variable to show that is just to monitor what I call the shape of my dynamically generated quantum geometry. So this is this non-perturbative ground state of my path integral. So what do you do? What we can easily, we have a kind of proper time that comes with the system. It's basically the time away from an initial slice, kind of proper time, at least that's the parameter of the theory. And we can easily monitor the three-dimensional volume of those slices as a function of t. So a typical snapshot would look like this. So anything, this is t, and then I look, at every one of my slices, what is the volume? So that's a typical thing. It's very surprising. Why? Because I told you, if you remember some slides ago, that I choose an S3 cross S1 topology. So this should be a cylinder, but no, it isn't. Kind of magically, it wants to be, as far as my kinematical gluing rules allow, it wants to be something else. It wants to be a compact space in a four-dimensional way. And how do we understand what it is? Well, we look at the expectation value of this shape, and that's what is done here in the ensemble. And what we are mapping it to, the shape in the sense of eigenvalues, is to a cosine cubed curve. And what is a cosine cubed curve? It's the volume profile of a Euclidean de Sitter space. Yeah. So that's what it is. These red things, they are not error bars. So there is a beautiful, very, very exact match of this shape to the shape of a classical, of course, Wick rotated Euclidean de Sitter space. And this tells you the red bars are the sizes of the typical quantum fluctuations. So would you say, okay, so you have, what you have is a de Sitter space. No, not at all. What I have is still a completely crazy quantum fluctuating thing. But if I pick out this particular observable, which would have, if I were doing cosmology, that would be the thing I would be looking for, right? Just the scale factor, the global scale factor. And it has a dynamically generated, shape in 3+1 dimension. And that's what it is. Can we nail down that it is really a de Sitter space? Well, if we were doing cosmology, of course, we would have thrown out all the degrees of freedom apart from this V3 or the A, the Friedmann scale factor. That's not what we are doing here. But why does one do that in cosmology? Because one assumes homogeneity and isotropy. Here we haven't assumed anything of the kind. So an interesting question would be to ask, to what extent are these universes we have there, can they be thought of as, on some scale, as homogeneous and isotropic? Well, you don't learn about what is the case by just looking at them. You have to ask the right question. And so you have to construct observables that quantify this statement. So you have actually, in a 2D toy example, constructed a non-perturbative homogeneity measure, which we've tried out in 2D, but which one would also try and apply in 4D. Cosine cube.
Yes, scale.
The scale cosine cube is, yeah. Yeah. Exactly. So in this case, so here is an observable that very naturally suggests to you a Lorentzian interpretation. Exactly. That's right. Well, look, of course, I'm doing all my experiments after I've done the Wick rotation. And after I take a continuum limit and put these things on the lattice, this alpha is not there for me because I don't have analytical control of this thing. So any Lorentzian interpretation of what I'm finding is a priori non-trivial, right? So I have to but in principle, but here, that's what I do in principle, but this doesn't exist anymore in my, as a free parameter in my. So that's a longer discussion, but thank you. So this is what happens. So briefly, I want to say something more. So we were saying, okay, non-perturbative physics, non-local observables. I mean, what are these things good for? Okay, so I already shown you some examples. So the dimensionalities is a non-trivial observable. The shape is a non-trivial observable. We can study fluctuations of the scale factor and their spectrum and compare this to a semi-classical formulation. And that also fits beautifully. But this is all about very global physics. Can we do better? And for a long time, there was no way to characterize local geometry in a nice way. And what you want to do in a way is to, what do we do classically? Well, geometries are, open again your GR text, but it's all about curvature. We think also of physical properties of space-time as captured by curvature properties. But on these Nova differential spaces, it's totally unobvious that any notion of curvature exists at all, or even should exist. So, if you have a non-smooth structure, here are our, crazy simplicial manifolds in some limit. Causal sets would have a similar question to us, or graphs. Can we associate a curvature with them? Now, it turns out that's a question that mathematicians have asked and answered and addressed in various ways. And this is part of the new mathematics beyond the smooth category that I'm talking about. So people have work in some, that could be called discrete mathematics, have worked in particular with interesting notions of Ricci curvature. So that's a huge field in abstract mathematics. So I'm putting down here some these new mathematicians, we've come up with a notion of Ricci curvature that's well defined on these objects and continues to be well defined in 4D in a continuum limit, unlike the kind of the deficit angle curvature that people typically use when they are working, in this type of regularized path integral. So that diverges infinitely. So the question is, if I look now at my, if I evaluate this, Ricci curvature is kind of a quasi-local construction on this de Sitter space candidate. What does it give? And again, the average curvature, again, this is very global, gives something that's compatible with the de Sitter space. But this notion of curvature now enables us to do more. So this is now the very last part of my talk. It enables us to define correlation functions. So what is the story of correlation functions? So let me first summarize what we have until this point: a lattice quantum gravity formulation that predicts the universe, as I said earlier, with a positive renormalized cosmological constant. It's 4D on large scales, something else on short scales, and this average shape and curvature, as I have explained, the experiments I can perform are compatible in the sense of expectation values with those of the de Sitter space, which is beautiful because it matches our current understanding of what the early universe is about. Now, observables that capture more local features, like the local fluctuations around these means, inhomogeneities, they do exist in this non-perturbative regime, and they're given by correlation functions. But since we are in gravity, and since this is a background, there's no background here to start with, there are diffeomorphism invariant correlation functions. So there are slightly different animals from what you're used to on a fixed background. In particular, when people perturbatively, talk about correlators, they usually work with kind of, some gauge fixed version of G mu nu G cover lambda. Well, we don't have access. We don't have any metric anymore. So the easiest scalar we can work with is a curvature, indeed. So like the Ricci scalar. And I told you we now have a well-defined notion of that. So that opened now this way of looking at curvature correlators. Now, so this is they're scalars, but of course, by same argument as R of x, at a point is not an observable. Here, we also have to integrate over the insertion points of the correlators, say the endpoint functions, x, y, etc., to make the final result diffeomorphism invariant. So, which is fine, but of course, we don't want to integrate over arbitrary x and y. We still want to keep track of their distance, right? I mean, that's interesting. That is an interesting piece of data we can still keep on to. But in order to make it geometric and diffeomorphism invariant, it must be a geodesic distance. So it's dg with respect to the metric g, say, of point pairs. If I look at what this boils down to for a two-point correlator, it's this expression. So O1, O2 are local scalars. So this is a formal continuum expression. Here's my sum ensemble average. Here is my the insertions, the integrals over the two insertions of the arguments x and y, where my scalars O1 and O2 live. And I throw in a delta function to make sure they're a distance r apart. Okay, so this is a bona fide diffeomorphism invariant correlator. Pure gravity, no external reference system. It depends on this r, this geodesic distance. And note here, of course, geometry is dynamical. So this g here is, of course, the variable you're integrating over. So you don't only have two geometric operators, O1 and O2, but what I call, there's a third operator dependence inside this thing here. So it's, again, a bit of a different animal. We get to it because we have to require diffeomorphism invariant. That this makes sense. I mean, these are ancient discussions, but what we can now do is really to show, so this is my next to last slide, that this can be implemented for this new curvature we have defined. One more point. This unusual dependence on the metric, which is a dynamical and not a background metric, leads to the fact now that if you are now constructing connected correlators, well, there are funny subtractions you have to make, because you would usually assume, right, the connected correlator is just the unconnected one minus, the individual averages. I mean, the bars are averages. Again, manifold averages have to appear because x and y dependence, has to be, it's gone away because of diffeo invariance. So, but what you see here is this interesting mixed terms, which have an O1, but this is not an O2, but it's a correlator of O2 at x with the one operator at y integrated over all xy's, which have distance r. So again, the fact that the metric is dynamical and not background, and you have this kind of third operator dependence, makes this look somewhat unusual. And if you had instead used a standard subtraction, only subtracting this O1 bar, O2 bar term, you get something that is nonsensical and that doesn't even converge to zero for large distances. So just to warn you, this is a two-point correlator, but interesting things happen that have to happen in a way because gravity is dynamical. No. It's all written down in a very nice way. So we've done a prototype analysis. I mean, this is just numerical because you cannot compute this even in 2D analytically, even in a 2D toy model. So we've computed it in 2D CDT, where you get very wiggly geometries, again, to tell you these are not nice in any way, not classical looking. And we've computed this curvature correlator. So this is a picture of what we do. Why are these circles there? Well, the curvature is extracted from a small neighborhood. So that's the size of the neighborhood, the radius delta around x. That's the size of the neighborhood, for some point y. You integrate over all x's and y's, subject to them being, having distance, geodesic distance r. And then you look at it as a function of r. That's what you would do. And then you would say, okay, if this is kind of standard, two-point function, there's some fall off which I can characterize. So what happens here, we are in 2 dimensions. So this is a curve, of a renormalized r, already kind of a continuum quantity, if you like, extracted, of course, in a finite size scaling limit. You see here non-trivial behavior, but this only comes from lattice artifacts. So where these quasi-local neighborhoods overlap in some way, and kind of there have to be correlations. But what we are interested in is what happens when these no longer overlap. So we have genuinely, local curvatures at different points. And from that point on, which you can quantify, depends on this radius, like here. Yeah, this connected correlator is just identically zero. Okay, very beautifully and very exactly. So what is happening here? Well, we are in 2D. Gravity doesn't propagate. So there's nothing, there's no interesting behavior in this propagator. What it shows you, it's feasible in 2 dimensions technically. I mean, this is not easy. I mean, measuring these correlators is not straightforward on the lattices, but we are busy generalizing this to 4D, measuring both kind of space-time curvature correlators, and we have relatively straightforward access to slices of constant time. And this is very interesting because in cosmology, when one talks about things like the power spectrum, they pertain to properties of the universe at fixed times. So we potentially have access to such a regime, but of course on Planckian scales. Yeah? So in the best of our dreams, what we can do here is to study this tiny system, maybe hopefully able to say something, extract from the space-time or spatial correlators, scaling properties, behavior of, how can we characterize these fluctuations? So again, they're not very perturbative for sure. Can they serve as kind of primordial seeds of structure in the way we usually set up things by hand when we do early universe cosmology? We assume a kind of de Sitter-like background. We have our, inflaton, and that creates little, fluctuations, and they induce gravitational fluctuations, and comes inflation along and woof, blows it all up. Here, this is purely gravitational. So I would say it's a very attractive concept. Can you come up with some predictions of purely gravitationally induced fluctuation spectrum? And you need a magnifier, of course, for this, to get from the Planck scale, which you cannot observe, to something like cosmological scales. So, but here is a genuine opportunity, it seems to me, to connect to real physics. So there are no analytical results to compare to, unfortunately, but maybe we can, because it's computations we cannot do, beyond lowest order perturbation theory in QFT on a de Sitter-like background. But we may simply skip perturbation theory. Okay, last slide before Benjamin kills me here. So key to quantum gravity, my main ingredients were the non-perturbative path integral. You're giving it nice causal structure, a geometric lattice regularization, and a numerical toolbox. I can do Monte Carlo simulation, I can do computations. It's a change of perspective, so it's a window on truly non-perturbative physics on the order, as I said, of 20 Planck lengths across, at the size of my universes. But it allows us to focus on concrete questions. So it's not just abstract arguing of what we would like to see if we only could. We study observables, and I showed you some of them. It's a very Einsteinian spirit because there is no background metric or reference system. So it really forces you to think in very geometric terms. And background and something like scale is only generated dynamically. So it throws new light, to my mind, on also what you might mean by solving quantum gravity. I mean, what are the questions we can meaningfully address with this particular framework? So if it comes to now this strongly coupled quantum regime near the Planck scale, if that's what it is, then what we're doing here on the lattice may be just the primary gateway to understanding its physics. So thank you so much for waiting to the end. And I await your questions.
Yeah, thanks a lot for this very interesting talk. In light of time, if there's any very urgent question and quick question, we can have it. Yeah, yes. Yeah.
There's some way to do a limited version of this, either by taking a limit, identifying the Planck system performance.
Not obviously so. I mean, really the covariance and the way we put these four-dimensional objects together is kind of key to producing this result. Yeah. Yeah, light cones, but what you are asking me is to identify in the kind of final result features like C. So how do light rays actually propagate on these things? And we don't have sufficient, let's say, if you give me the nice observables, that tells me it's a Planckian implementation of this question you're asking, we might be able to study it.
Okay. Thank you. Let's thank Renate again. There will be plenty of time later